say anything about it or not.
Mm.
But yesterday I think you showed the BMS
Yeah.
HIL using the Orion BMS. I'm quite familiar with that BMS. So just want to know, how did you connect the BMS with the HIL? Because, and especially the current sensor, because I think the BMS comes with current sensor. So how did you simulate the current for using the HIL?
Nicola, can you jump in and just briefly explain? I think. Um,
Sorry, can you please just repeat your question?
Yesterday you showcased the HIL simulating the current and the voltage. So I
Okay.
just want to know, because that BMS comes with the current sensor. So how did you able to produce the simulated signal for current and voltage? Like, because how did you do the connections from the BMS itself to
Uh-huh.
the test bed?
Okay. So basically what we do is, we have a simulated current value. Of course, dependent on the charger that we have in the system. For example, I'm just talking about the charger current. Then this simulated value, the digital value, a number, uh, we can output it on our analog output of the HIL device in the form of a voltage signal. Now, the HIL device itself has a limited, a fairly small output voltage range on its analog outputs, so it's plus minus 10 volts, while the current capabilities are even smaller because, we're not producing power with the HIL. So what we do is actually we take this current signal, we provided this voltage on the analog output, and then using an interface, so this is the HIL Connect, just this HIL Connect box, one of the boxes that you were able to see there, we can actually take this voltage, and then if needed, if the BMS requirements require a bigger range, a smaller range, we can either use analog output cards where we can scale up this voltage to a larger value, or we can use current output cards where this signal can be then transferred as current. So it all depends on what your BMS and how does it, what kind of an input does it need for the current signal. So it's kind of a mix between, something that we take from simulation and then something that we output through an interface card.
Okay. Hafiz, are you
Yeah,
clear? Yeah.
yeah, clear. Yeah. Right,
All
thank
right.
you.
I think so. Today we are going to talk about the e-drive, and I think the presentation and the demo is meant for that. Nick has joined us. Welcome, Nick. I guess we can start. Yeah. So, Militant, you can take it over. I think you're muted.
Thank you, Nick. My bad. I didn't notice that I was muted, but thank you for the kind words. I guess we had a nice discussion yesterday about where Typhoon sits in the e-mobility space. What applications do we cover? What's our niche, and how we approach the market differently than our competition. I would like to repeat some of the stuff so they stick better to the Perodua team. They fully understand. Uh, where our proficiency lays at, and just so our team will be fully aligned on where Perodua sits currently. They're exploring of producing their own and developing and producing their own components for the electrified powertrain. So one of the topics was BMS, the other ones are e-drive, so inverter plus the motor. Up until now, they were they were sourcing that equipment from the tier ones, so not developing that themselves. And previously, if I understood correctly, Nick, please correct me. Peredua team hasn't used HIL equipment at all in their testing and development life cycles of their products. So um, I guess today, so I'm just gonna briefly, like 10 to 15 minutes max, just to cover, again, the basics about Typhoon Hill eDrive solution, how the racks look like, how the equipment, what's the equipment inside, and then I would give the word to Rajashi, so our application engineer sitting in Bangalore. He's gonna cover demo of the software and the drive application, and then we can open up the whole discussion. Again, as yesterday, please don't hesitate to interrupt us at any moment. So please shoot with the questions. Let's keep the discussion interesting, let's say. So let me know when you can. Do you guys have any questions before I share my screen?
No, I think you can go ahead.
Mm-hmm. So I'm not gonna start from the beginning because you've seen the slides, how we started and where we located. But again, so HQ in Boston, uh, big sales office in Switzerland, biggest R&D and production in Novi Sad, Serbia, with the locations. So a new office in Bangalore, Japan, with the wide network of value-added resellers and distributors, such as Marcus, so that are adding value to our whole tool chain. When it comes to e-mobility applications, so we specialized. I mean, even before e-mobility, our software specializes for high fidelity hardware in the loop solutions, focusing on demanding applications with high switching frequencies. We decided to move to e-mobility when automotive became electrified, and bringing in more power electronics component with it. So in the e-mobility domain, we cover applications and testing of all the components of the electrified powertrain, and we specialize for the ECU testing of the eDrive, onboard charger, DC-DC converter, BMS, and similar, and HVAC applications. So this is our bread and butter, and this is where our specialty lays in. Again, we've covered some of those slides yesterday, but it's always good to remind what's the how is Typhoon different than the other competition on the market. So with our general solution approach, since we are vertically integrated, meaning that we provide hardware, software, and engineering services unlike the other providers. So software is ours, and that comes with many benefits, let's say. So when you're creating the model in our software, the creation itself is very easy because we've developed, and our software comes with a very rich library of pre-compiled blocks that are designed to run on FPGA. So you just drag and drop, parameterize, click compile, and compilation time is very quick. So any modification or extension of the model is very fast, unlike, let's say, with DSpace. So you don't need to have any FPGA coding knowledge in order to design each component and then deploy it to the FPGA, and that process itself is very tedious and it consumes time. Comparing to that, our let's say compilation time, even with the complex models, is a couple of minutes, and with others, it's a couple of hours. This just proves the point that with our solution, you actually focus on testing and developing your solution rather than playing around with the environment, getting the system up and running. And on top of that, just the using and the user interface of the whole system is very, very easy. So your team, like we usually do, so if you purchase, let's say, eDrive testbed, we come on site, we do the commissioning, and within 7 days, your team, or 5 days, so one work week, your team is running full speed. So the next week, your team is able to autonomously do their own testing. Of course, we're going to be there along the way to support you. So even that, if people didn't have any knowledge or skill in using HIL technology with our solution, it's really easy to get people onboarded and actually start producing results right away. So um, mentioned most of this time, most of these things, but again, so we are built for HIL testing of power electronics components in the electrified powertrain. Uh, you can find especially for the eDrive applications, you can find very rich library of components such as motors, inverters, converters. So really everything that showed up in the market up until now, it's available in the library. So there's no, complications with that. You just drag and drop, parameterize, click compile, and then off you go. We So when it comes to how the whole solution looks like, is I can I'll show you again the how the eDrive testbed looks like. But okay, so we provide the HILs, the racks, signal interfacing devices, fault insertion units, and that's on the hardware side. On the software side, our solution consists of, let's say, so our platform is called Typhoon HIL Control Center, and there's three main elements in it. So schematic editor, HIL SCADA, Typhoon Test IDE. In the schematic editor, this is where you draw your model, parameterize your components, uh, draw your whole schematic, pretty much. Uh, After that, after you click compile and run your simulation, you're building the interface in the HIL SCADA. So that's where you're interfacing with your simulation, building all sorts of GUIs, capturing data through all sorts of tools, virtual oscilloscopes and similar. And on top of that, everything that you can do in terms of collecting the data and interfacing with the simulation itself manually in HIL SCADA, all of that can be done in Typhoon Test. So our test automation platform that's based on Python. When it comes to, I don't know, oh yeah, when we talk about more specifically about eDrive ECU, ECU testings. So okay, typical eDrive consists of inverter and a motor model. And when it comes to inverters, so we provide you with high resolution model with 3.5 nanosecond sampling rate, which is very suitable for high switching frequencies. Of course, we can simulate and insert the data for the forward voltage drop, turn on and off delays, and real-time power loss calculations. When it comes to motor model, we provide you with nonlinear saturation model, spatial harmonics, and if you're doing some using some finite element modeling software such as JMAG or ANSYS, Altair, so we can use that data and the parameters can be imported via 3D lookup table into our software. Of course, I mean, we can also do the thermal modeling, fault injection, and integrated position and speed feedback through resolver card. On topic of how the actual typical eDrive solution looks like, I mean, this is it. So it comes in an industrial grade rack, and I'll just gonna name some the components starting top to bottom. So on the top you have main power supply unit. Below it is our it's DC power supply that's used to power the DUT and provide potential lines for battery voltage, fault potentials that can be later inserted through the fault insertion unit into your DUT, into your circuitry, and that way you can test your reaction or your devices and software reactions to the faults. On the top, you have the brain of the system, so HIL 606, where the whole math and the simulation is being run. Below it, since the HIL has the let's say a signal range plus minus 10 volts, so if there are any signals outside of that range. We introduce a signal interfacing device with all sorts of cards available already designed, so digital and analog inputs and output cards, resistor emulations, resolver cards for motor positions, relay cards, and similar. And on the bottom, of course, as I mentioned, so breakout box are fault insertion units, so meaning physical fault insertion, so we can simulate, all sorts of, let's say, interruptions, so short to ground, short to battery, uh, short circuit in between two lines. So everything can be physically be simulated, not simulated, physically inserted into your DUT, and that way you test your software and DUT reacts. And with that, you are in compliance with ISO 26262. So everything is covered with this solution. Again, we talked about this. So the brains of the system, and where everything's being done, is HIL devices are offering covers three main devices. So HIL 404, 506, and 606. The difference between those two is, processing power of how big of a model can you fit on the FPGA. Usually for eDrive applications, so just inverter and the motor, even 404 is enough, but then you're adding different stuff in the equation. So the devices differ in terms of processing power, number of digital and analog outputs and inputs, and the communications. So HIL 404 is limited in terms of IOs, and it doesn't have CAN-FD, for example. So if you're talking about if CAN-FD is a must in your process, then we would go with HIL 506 and 606 or 606. So just to briefly touch upon the modular HIL Connect, so our signal conditioning interfacing device. So it comes in a 6U metal chassis, and it can fit up to 8 different cards in one device. So it's usually, for the standard eDrive configuration, we have one analog output cards with a range of plus minus 24 volts, analog output card, digital input card, digital output card, a resistor emulation card to simulate the temperatures, and the relay card. When it comes to breakout box, we have 146 channels, and they're software controlled. The whole fault insertion is software controlled, but it actually is physical fault insertion. So the actual fault line is supplied to the breakout box, and you insert that fault potential into your circuitry, and you have access to all the system signals on the front panel, meaning that you can physically attach the oscilloscope and actually check what's going on there. With that, I wouldn't want to bother you too much. I would give the word to Rajashi to flash his screen and show you the software and the demo again, specifically on the e-mobility demo, so eDrive demo. But before we jump into that, do you guys have any questions up until now?
Nick and Cheryl, do you have any questions? And also Hafiz?
So far no. Okay, please proceed.
Okay, I have one question, Milutin, if I may. Yeah, because
Please.
in my discussion with Perodua, as you know, their aspiration is to develop their own controllers, their BMS, VCU sometime in the future. But in the interim, they are getting the controllers, the VCU, the BMS from tier 1 suppliers. Can this test bed, the eDrive HIL, the BMS HIL test bed, can they act like some kind of a tester where they can plug in their controllers, all right, their VCU, and test different fault scenarios to validate that it actually worked, or they can program different scenarios that is unique to the Malaysian environment, okay, and then test the VCU and the BMS. Can it act like a tester?
Yeah, I mean, you're talking about like end of line testing or, a step before that. So the whole point of our HIL is to test and develop the control software of your ECU. So if
Okay.
you're not gonna play around, and develop your control software on the ECU itself, I don't think that's the right use of our tool. But Jovan, please correct me if you have something, in addition to that.
Mhm. Yeah, I mean, it depends on several factors. So I would say that the first thing that we must know is whether this ECU that you get from a third party supplier, you need to have an access to it. So do you get an ECU only, or you get, for example, if we are talking about inverter application, you're getting an inverter as a black box, and the ECU is essentially just a part of this black box. So this is very important. So the first condition that has to be fulfilled is that you have the access to ECU only,
Mm-hmm.
and you can actually then put it into a setup like this. Now, when you put one thing is that if you are buying, let's say, a motor inverter from the supplier, then this sort of software testing should already be done by the supplier, and the inverter should be certified in accordance with all the relevant standards. So then maybe you could use our equipment if you just want to do some kind of a bring up on the ECU. But again, I agree with Milutin. So the
Mm-hmm.
the idea of our equipment is to use it to validate the control software. And again, I mean, if you are buying something as a product from someone else, you would naturally assume that the software is already tested. So
Mm-hmm.
then what
Okay.
you're looking for is maybe something for, let's say, integration. Again, our simulations can be used for that, but again, that's not our focus here.
Mm-hmm. Okay, good. So as long as they have access to ECU only, right, then they could actually develop using the eDrive Hill.
Exactly,
Yeah.
because if
Yeah.
you don't have the access to the ECU on its own, you
Yeah.
need to have a power hill pretty much, right? So you have an
Yes. Yes.
inverter and you connect it to something. For us, this is not something
Mm-hmm.
that is interesting.
Sharil, and Nick, maybe you can advise. Do you all have just access to the ECU only?
Sorry, come again?
Um, your eDrive, right? Do you have access to just the ECU only, or when you buy the product, it comes with the inverter as well?
Of course, we at the moment we are outsourcing this EDS or
Mm-hmm.
EDU. But
Mm-hmm.
then, of course, in the long run, how do we do it in terms of localization
Okay.
or something? This one we will how to say? We
Yeah,
will
you will
study.
explore.
Yeah, explore.
Okay, can.
Mm.
So, thanks. So, I will not hold you up. You can proceed with the demo, Rajesh. Thank you.
Hmm? Okay, cool. Please,
Yeah,
Joshi, floor is
yeah,
yours.
yeah. So I will just share my screen. Is it visible?
Yeah,
Yep.
Okay.
all good.
So I see that the team is already well versed with the tool. Still, I will go with the entire demo of our tool chain, all the two our tools we have. So this is our software, Typhoon Hill Control Center. It has three main tools, as Milutin mentioned. Schematic editor, which is mainly used for building the models, like building a power circuit, building a signal conditioning circuits, etc. in the canvas. Then we have the HIL SCADA tool, where you can monitor your signals like voltage and current in real time and also regulate other variables and parameters in real time by directly communicating from the PC to the HIL device. And then we have a Typhoon Test Automation IDE, which is a Python-based IDE where you can code your scripts in Python and like code hundreds of different test cases and keep it running overnight and have the results ready at your disposal. So the schematic editor, if we go, I will start with a blank panel to show you the ease of use or how easy it is to onboard to our environment. So we have a custom made library where we have segregated all our components into different categories like converters, machines, sources, microgrid libraries, etc. So one only needs to open the library and bring in particular components like maybe the converters, the sources. You can also double click and type the sorry, double click and type the name of the component and it will come up. So for in case of voltage source, you can bring in a voltage source and just connect them by simple wires. So if that's easy to make a circuit here in the schematic editor. It's a blank canvas and you drag and drop the components. So for this demo, we are considering a PMSM setup, drive setup supplied by an inverter connected to a DC source. So before coming to this, I will just show the uh, C-Hill like controller hardware and loop test bed. For that, I will just open my camera. Yeah, so this is the test setup which I have on my table right now. So all the power circuit is being modeled inside our HIL device, and all the control circuit for is being modeled into the controller. For that, we are using the F2 Ti C2000 F28790 controller. This controller is interfaced to the HIL device using an interface card. This one. This card is also developed by Typhoon. And if you have your own separate controller which you would like to integrate with the HIL device, you can. We are ready to support in helping you integrate your custom-made controller to the HIL device. So I will leave this on and continue with the demo. So going to the power circuit, we have a DC source on one end and an inverter, which comes from the converter library. This inverter is custom made and like not custom made, is optimized to be well suited for operation in the FPGA. So all the state space calculations have been done inside and a custom made block has been given for you. So inside this, you can control how the gating signals to the switches will be generated. If you want to test your own controller, so you can take the gating signals from like as a digital input for switch or digital input per leg. If you want to just test your topology or modeling of your circuit here, so for that you can directly use the internal modulator or the model based control where you can develop your control here inside our Typhoon Health software using signal conditioning blocks. Then to increase the fidelity of the simulation here, we also have a lossless tab where you can include the device characteristics of your switches which you are using on the inverter. Suppose IGBT, then in the case the IGBT and diode characteristics can be input. One using the XML files of the which is available in the datasheet from the manufacturers by directly importing them. Or if you don't have this, you can manually populate the characteristic here by using lookup tables. Similar thing can also be done for a MOSFET with the integrated diode. Going further in the power circuit, we have a machine. So we have a dedicated library for machines here, so which is quite extensive, in which here we are using a synchronous machine. For that also we have a large set of libraries. So suppose you are using a basic machine and not any custom made thing, you can bring in our basic machine component and model the electrical, mechanical load parameters according to your specific need. Suppose you are using some separate third-party tool to model the dynamics of the machine, like the magnetics, etc. We have components like the one here, the JMAG PMSM, where you can import your JMAG RTT file to emulate the dynamics of your JMAG software inside our ecosystem. Similar kind of tool is also available for ANSYS, where the ANSYS EC file can be imported here. So in this just I mentioned for your reference, like the versatility of a tool chain in co-simulation with other softwares. So coming to this machine component in detail, other than the electrical and mechanical parameters, we also have the encoder and resolver feedbacks, wherein like in any physical motor drive setup, there is an encoder or resolver connected to the shaft of the machine. So we provide that feature where the encoder digital data or the resolver analog data is transmitted to your controller from the HIL device to the controller through the respective digital or analog pins, whichever is used. So in this example, we are using an encoder, and I will show you the encoder A, B, and Z signals are being transported over digital signals. So if you have a look, and so this is all about the power circuit. You might notice that there are some black and blue colored blocks. So all the black colored blocks represent the power circuit, which is flashed into the FPGA of the HIL device, and all the blue colored blocks, sorry, yeah, and all the blue colored blocks are the signal processing blocks, which are simulated inside the system CPU of the HIL device. So one such part is the mechanical aspect of the drive. So in this case, as in an E-drive example, we have modeled the vehicle mechanical dynamics in a subsystem by making some simple mathematical calculations using signal processing blocks. So for that, we have used the torque of the machine, and using some calculations generated the mechanical speed of the shaft, which is again then fed back to the machine just to create a closed loop between the load and the electrical drive. Other than that, we have some power and efficiency calculations being performed here in using signal conditioning, and some other measurements of RPM, electrical speed, rotational position, etc. Like in this case, we are using a controller hardware and loop setup. So we have a tool called as the automatic code generation tool, which we are supporting for a certain set of TI-SU 2000 cards, in which, like, these are the cards, control cards, which we are supporting. So in this, what you need, if you don't want to do custom coding of your C coding in the dedicated software of the TIC 2000, we have a provision that, okay, you develop your control within this Typhoon Hill toolchain using the same signal conditioning blocks, C functions, etc. And then you interface with some pre-packed TI blocks, like here the DO blocks, digital output, some serial communication blocks, some ADC blocks wherein the measurements of the currents and voltages are coming from the HIL device to the controller, and the EPWM blocks where the PWM signals are being generated and sent back to the HIL device. So you just,
sorry,
yeah, yeah.
Rajesh, sorry. This prefab blocks is what do you mean by prefab block? Meaning, is it we need to develop by our own, or is already in the?
No, like these are custom made blocks available for the TIC 2000 library. Suppose you are using the TIC 2000 controller, then if you want to get in some analog signals, so there is some code. You have to follow a particular structure of code. So we are saying that you need not write that code. These are simple generic blocks where you just mention the port number, analog output port numbers, the scaling and the offset of the signal which is to be coming, and that's it. You'd get the signal here. So this entire control code, we'll be flashing it to the controller here.
Meaning if we have this, what is the model? We already have this kind of block, is it, in the library?
Yeah, yeah, please.
Yeah, let me just jump in quickly. So this, what Rajarsh is showing now, this is only in case you are just developing your controls now. So this is completely separated from the simulation. So in case you are developing your controls, you can use our environment to generate the code for your controller. My understanding,
this is a custom. We need to develop this if we want to make our own controller.
No, exactly. So in your case, this feature is not really interesting. So I propose we can skip this. Just the idea is that we used our own tool chain as well to develop the control so that we can show you the simulation capability. But this feature is not really something that you would be using, since you already have a custom controller. So we can skip this part. This is a feature that's not really interesting for you.
Okay.
So what in this case I have done is I have made the control and flashed the control code using some clicks of a button, and now I have disabled it. Like, this is the enable condition. I have disabled it, so it's like grayed out. So now only in the entire circuit, the power circuit is mainly present and some signal processing blocks. At the bottom, we have here some voltage and current analysis where we are taking the ABC voltages and getting the respective DQ voltages. Yeah, another thing I think I missed out probably in the inverter section. So as part of the losses tab, where as you whenever you model the losses in the inverter, it generates the total losses of the inverter, and we have the capability to also model thermal losses. So for that we have a thermal model of the heat sinks, for which you can choose the type of network and get the various total losses and case temperature, etc., and also the junction temperatures of your switches and diodes. So this is, I think, all about the, yeah, this is all about the power circuit here. So the best part of our toolchain is you need not be an expert in FPGA. So all things are pre-compiled and custom, very nicely optimized to be simulated on the FPGA. So if I just hit validate and compile, it will compile in a couple and just under a minute to be ready for simulation in the HIL device. So now if you see the bottom tab here, the compilation is going on. So the steps it follows is first it validates the model where it checks for any open connections of the machines or converter or any short circuit in something. And then it compiles the entire model, which is the exact code which is to be dumped into the FPGA. So we will wait for a couple of minutes here. Not couple of minutes, like a few seconds. Yeah. So I'll just show at the end, very end. So compilation finished successfully. You can see all the data like how the compilation has done. So this is something which can be used later if you are debugging the system. So next, coming to the SCADA panel. This is again a similar thing. I will open a blank SCADA panel just to give you a feel of what it is. So it's a blank canvas. You can bring in various widgets like checkboxes, text boxes, sliders, knobs to control various parameters in real time from the PC, and then to observe the other variables like voltage and current. We have capture scope available where you can like put in the signals and capture the data here. Then we have other displays like text displays, gauges, LEDs. So this makes the entire panel quite user friendly and quite easily to accessible, visual friendly in real time. So this was just an example. We already have a pre-custom custom pen panel for this example. So I will just make the model running and then start. Yeah. So as we see, the HIL device is connecting with the controller, and we also have a communication between the controller and the main host PC, where in for which we are using a serial communication. So I will enable the serial communication, and initially the E drive setup is working in speed control mode. So if I change the speed of the machine to 8000 maybe, yeah, so it will automatically track the speed of the machine. Here if we see the inverter like thermal data has been showcased here, wherein the temperatures of the switches and diodes have been showcased. And suppose I go to the torque control data, then if I put in 20 reference, then yeah, the torque is now been controlled accordingly. I'll go back to the speed control. I'll show you the other parts of the setup. As I showed in the capture scope widget, you can capture your voltages and current signals, like in observing, like in a simple similar to a practical DSO. You can also capture this with the frame which you want. You can set that, okay, I want to capture for maybe 0.2 seconds at some sampling rate of 1 mega samples per second, and just force trigger, and you will have the results similar to your scope. You can use them to put them in your reports and etc. We also have a feature of enable trigger with some sources where you can use different sources to trigger accordingly ups per your needs. Going further, we have this custom made dashboard where the speed of the vehicle, the has been like the vehicle mechanical model which we did, kind of relating to it. We have populated the speed of the machine, the distance covered, the electrical torque, and other parameters here. So these all can be done. And these are the DQ parameter data of the voltages and currents which can be visualized here. So yeah, and the best sorry, another thing I would like to mention that as part of CHIL testing, you are free to do any kind of testing here. Like you have the access of changing in all the SCADA inputs, like the machine data, the angles, etc. The source data. If you want to change the voltage source
Sorry,
values in real time.
sorry, what is SCADA?
SCADA is I would say, a real-time tool where you can monitor your model from the host PC.
Okay.
Is it okay? Yeah. So now you can also inject faults. Like suppose you want to say that okay, one of my switches is not working, or what will happen if what how will my control react? So you can inject in some for like switch faults by okay the switch is zero for all the time or one for all the time. So all things can be safely done without doing any damage to your actual system or actual controller when using the CHIL setup. So I think that's all about it. I leave it to you all for questions.
Okay. Mr. Sariel, and Nick, do you have any question? So SCADA is actually what you're saying now. This control panel is called SCADA.
Okay, okay. Adi, please ask question. Oh, no file.
Hello.
Okay, Adib, huh? Yeah.
Actually, I want to explain my situation. Currently,
Yes.
we already have the motor from the supplier. So let's say our motor, e-motor, currently we have some kind of NVH problem, which is we detect some noise inside the e-motor, and then we want to do some simulation, and we want to determine what causes that noise comes from. So by using HIL, can we do some kind of that simulation, or is it only for the control system?
HIL, so controller hardware in the loop, is intended to test the control software and the software in general. So if you have some noise coming from some mechanical device, controller hardware in the loop is simply not the tool that you need.
Okay. Because from my understanding, we need to do some calibration in the motor controller. So maybe we can use this HIL or
Yeah, I mean the main question is okay, are we dealing with something that is a hardware issue, or we are dealing with something that is a software issue? Again, I mean, if I'm buying an electrical motor from someone and I have an issues, I would go back to my supplier and just say this thing doesn't work as intended. That's it. Um, Again, if you think that you should be changing something in the software, you can always check the software itself using HIL. But generally speaking, then I'm not sure what the arrangement is. Is the software something that you bought? In that case, it should be functional on its own, or is it something that you are, free to fine tune? Because then again, the question is whose software this is.
okay, understood.
Okay,
Okay, thank you. Nopal?
Mockup first. So kita nak tengok kemampuan dia orang by mockup punya label lah. Tapi equal to F.
No, for now.
okay. Thank you, Rajarshi, for the solid demo. I don't know. I think this, I don't know, moment in time of your development and idea of starting to use HIL is not fully mature. I guess So I think we should, restart the conversation when you actually get to the point and at least deciding that you will start developing your own components, meaning that you have the teams who will develop the control, who will develop the software, and our tool again is used for testing the control software of electrified powertrain components. So uh, all the other variations that you had in mind, it actually that doesn't. So the our HIL or any HIL is not really the right tool for what you had in mind. So until we get on that point in time, I think it's an overkill for what you guys are doing right now.
Yes,
But please.
it's okay. It's okay. I think what you is actually what you are explaining to us is actually also a useful information and exposure for us. But then we of course we still how to say new in this microcontroller control unit, especially for motor, but for e-motor. But then of course don't we still appreciate your explanation just now. But then we will keep in touch, of course, if we have any progress or some updates.
Of course. I mean, we will be at your service, no problem at all. Ready to help you out, but um, let's just get some at least checkpoints in line or straight to when is the right time to start using HIL. It's never too early to discuss things. I mean, that's why we did the demo and the demonstration. But some things in your, let's say, a development or a plan have to mature in order to even start using the HIL.
Yes, of course. I'm sorry, maybe it's not, of course, not this year, and then maybe also maybe not for next year. But then we are looking at a possibility, maybe around 2028 onwards.
Yeah. Okay, great. Awesome. Let's keep in touch and
Okay.
keep us updated. Awesome.
Okay, thank you. Okay, thank you.
Thank you guys very much for your time.
Thank you very much, Milutin and Tim. Thank you, Perudua. Thank you.
Thank you.
Thank you all.
Bye.
Bye.
Thank you.
Thank you all. Bye.
Bye. Bye.
Thank you.
Bye. Thank you, everyone.